Welcome back to Quay Does Leetcode. Today I'm going to be doing problem number 235, lowest common ancestor of a binary search tree. Now, an important thing about this question is that it is a binary search tree. So, a binary search tree has special properties, namely that if you look at the root of a binary search tree, every element that is in the left child, every element that is in the left subtree is less than the root, and every element that is in the right subtree is greater than the root. So that's a binary search tree, and that definition is recursive. So for every node, that is also true. So for this node here, every element that is less than it in the left subtree is less than it, and every element that is in the right subtree is greater than it. So it also is true for every node. So that's a special property of a binary search tree. That's basically what a binary search tree is. So what are we supposed to be doing with this binary search tree? Well, given a binary search tree, find the lowest common ancestor of two given nodes in the binary search tree. So we're given the nodes in this example, P equals 2, so this node, and Q equals 8, so this node, and we're supposed to find the lowest common ancestor. So the lowest common ancestor is the lowest node in the tree that has both P and Q as descendants of it. So you can, and a node can be a descendant of itself. So we can see that the only node, which is the lowest node in this case, that has the ancestors of 2 and 8 is the root. The root has 2 as an ancestor, and it has 8 as an ancestor. And so the answer is 6. For another example, we can see this tree. We're given the node 2 and we're given the node 4. And 2 has an ancestor of 4, and 2 is also a descendant of itself, so the answer is 2. So looking at the tree, we can determine the lowest common ancestor, but how can we do this programmatically? Well, remember that this is a binary search tree, so that means that every element to the left of the root, or whatever node we're on, is less than it, and every element to the right is greater than it. So we can see a pattern emerges that what if we were looking for the greatest common ancestor of nodes 7 and 9? Well, the greatest common ancestor would be 8. It would actually be the point at which the tree branches off. So it would be the point at which the tree branches off. So when the value, so when you're looking for the lowest common ancestor, you will either be finding both the nodes, both, well, you'll either be finding both the nodes we're looking for to the left, because you'll either find them over here if they're both less than the root, in like in the case of if we were looking for 2 and 4, or you'll find them both of the nodes to the right if they're both bigger than the bigger than the node. You'll find them both to the right, or you'll find them, or one is to the left and one is to the right, and that is when you found your or found if one is to the left and one is to the right. And also, if one happens to be, if we were looking for the nodes that we were looking for the greatest common ancestor of were 8 and 7, well, one is the same. One is the same. So if one is the same, then that is actually the answer. So found if. So there's 4 cases. So you can actually you can traverse the tree, and you can start at the root. So say I'm looking for the lowest common ancestor of 8 and 7. I start at the root. Okay, now I can either find my nodes to the left or to the right. They're not to the left because 8 and 7 are both greater than 6, so they're both going to be to the right. So I look to the right. And now I'm on 8 and 7. Now one of my nodes is the same as the current node that I'm on. Now I'm on node 8, and the current node I'm on is the same as one of my P or Q nodes. And so that means I found the lowest common ancestor, and it's 8. So that's how it works. So let's go through a couple more examples so you can see a couple more cases. So what if 2 and 4 were the nodes that I was trying to find the lowest common ancestor on? Well, I start at the root node. I start at 6, and I can find both of my nodes to the left. So I look to the left. And then I'm on the 2. Now one of my nodes is the same as my P or Q, so I found it, and it's node 2. And now finally, what if my nodes that I were looking for were 2 and 8? Well, I can't look to the left because one of my nodes is to the left and one of my nodes is to the right. So if one is to the left or one is to the right, then I know that I found it. And the answer is 6. So that is the algorithm for solving this problem like I said, there are 4 cases. You keep traversing. If both of your nodes are to the left, you traverse left. If both of your nodes are to the right, you traverse right. And if one is to the left and one is to the right, then you've found the answer, which is the current element you're on. And if one is the same, then you've also found the element that you're on. So let's code this up. So for this, we can actually use a an iterative traversal, and we don't need to have a stack because we don't actually need to get anything from. We just need to just traverse down, and we don't need to return anything upwards. So we don't need a stack for that. So we can just traverse. So we're going to start at our current node. Is going to start at the root. And while our current node is at a node, we're going to check if current.val. So first we're going to check if both of our nodes are to the left. So both of our nodes are to the left if p.val is less than current.val and q.val is less than current.val. And that means both are to the left. So that means we're going to make our current equal current.left. So we're going to move to the left. Else if our p.val is greater than current.val and q.val is greater than current.val, then we're going to move our pointer to the right, because the answer is on the right. So if neither of these are the case, so there's 2 cases that are covered by this else statement. Else, this is going to mean one node is on the left and one node is on the right, or one is equal to current. If either of those are the case, then we found the answer, so we're going to return current. And we're guaranteed to find an answer, so we're guaranteed to hit one of these points at some point. So that is that's the way you code this up. So let's run this, and we're getting the right answer, and let's submit, and it was accepted. So that is how you find the lowest common ancestor of particularly of a binary search tree using the properties of a binary search tree. And this algorithm runs in O of n time, because if all the nodes were left nodes or right nodes, you would have to keep traversing through. If it was a skew tree, you'd have to traverse through all the nodes, and it doesn't take any space. It's O of 1 space, because you only need a current pointer. So thanks for watching, and I'll see you in the next video.